Welcome aboard, it's Friday again. You're back to Cortina City, and we left you last week messing with the Crypton Tuners. And here they are, beginning our repair restoration. We've got to pick which one gets the treatment, and it's looking like it's going to be the larger model. First things to do is to see where we are electronically on these, and we begin the investigation of the electronics. That starts by pulling out the control box for the scope. Now, we've initially had a little bit of power to this, and I did get a trace on the scope, although it was compressed, switched off because it didn't look good and it was starting to get hot, the control box. So I'll take you over to the control box now, show you what I mean. This is the heart of the Crypton's scope. Also controls a few other things as well, but this is the main brain behind it. All valve controlled, no microelectronics, no solid state stuff. So it's all resistors and valves, and that is how it looks inside. This is just an oscilloscope, that's all it is. And we're going to talk to you about oscilloscopes and what they actually are, and a few little electronic and techie lessons in this video today. So what we have to do is say to you, this is a tech vid. We may go out on the road just to collect some electronic parts that are going to be needed, but essentially this is a tech vid. We'll be talking about what an oscilloscope is, in case anyone doesn't know. We'll be doing some basic electronics. We'll talk about valves and electronic components that we need to be looking at to get this thing going. So at the moment, as it stands, it has got faults. It isn't displaying properly, it's getting hot, transformer's getting warm, too warm. We're going to get it back powered up after I've replaced a few components on it, and I'll show you how we do that and what we're going to do to try and diagnose the fault on this. My background is in digital electronics. This is analog, and I've never worked with valves before, but it's the first time for everything, so I'll begin to take out some of the parts, and we're going to talk about what's actually happened. Immediately we found a damaged valve in this. Immediately we found a shorted out capacitor in this. It's now been removed, it's dead short. I've found some resistors that are open circuit. So I've been going through with the meter, and we'll be looking at replacing the capacitors in this. These are the capacitors here. They're all dotted all over the place, and they're renowned for, over time, deteriorating and creating a lot of leakage and not doing the job that they're supposed to do simply because of their age. They break down. So really, before we even try and get this set going, it's very good practice to go through and try and find equivalent parts and replace them out in terms of the capacitors and the resistors. Certainly with some of the high ohmage resistors, they tend to be the ones that go. So we're going to get through with a meter, check all that out. I have done some checks and I've made some notes along the way off camera, and these are all the resistor values in the book. So I now go and collect all brand new versions of those, the closest equivalents we can get from CPC. Also, we need a couple of other things. We need an isolating transformer, because what we don't want to be doing is running this straight off the mains when it's on the bench being tested, at least, because you've got rectified mains, you've got a lot of high voltages in here which aren't good to be working with. If you accidentally touch anything, you connect it across the main, so we disconnect from the supply. Someone's already been in here messing with it because there's tape on the mains input wire. We're going to have to go through all of this and get some safe operating practices going. Some equipment is going to be needed to pick up. We need an isolating transformer, we need a Variac, because we've got to bring up the power slowly. A Variac is a way of bringing up your mains very nice and gentle. You can start from no volts and you can go right the way up to 240, and that helps when you're starting to replace parts on this, to bring power in nice and gradual. and it'll withstand that, so you can help to not shock it and not make it suddenly blow another part. So you bring the power up nice and slow. So what we've got to do is get some safe working practices up and running, because we're talking about high voltage here now. It's a different ball game than what PC's been used to with electronics, microelectronics. You're talking high voltage, you're talking dangerous levels of voltage, boosted levels of voltage, because the oscilloscope needs that, or the television screen. It's not strictly a television screen, but we'll talk about all these things. I appreciate that a lot of people watching are not coming in from an electronics background, but may well be interested. And I think there's nothing wrong with learning, so you may as well learn. Off we go. We're out on the road and get some parts first, and we'll come right back and I'll talk you through how we're doing it. Simultaneously, at the same time, I'm building a speed control circuit for Project Ruby. Speed control to control the torque lockup. At the moment, Ruby's torque lockup is done manually, and we've been so successful with Bramble's speed controller that we built, and the VAC switch controller, that we're going to clone what I did off this car. Now it's tried and tested technology, and apply that to Project Ruby, so Ruby gets a fully automatic torque converter lockup instead of me having to manually switch it in. The parts for that are in stock. We've already gone out and got them all. They're all here ready. I've put them all into the trays. There's a circuit diagram that I've got, which we're going to build a speed controller. We're going to show you how we build a speed controller, how it connects to the VSS, vehicle speed controller, on the back of the gearbox. These signal pulses that come in that are used at the moment on Ruby for the cruise control. We're also going to be using them to activate a 40 mph speed switch. So when the car's doing 40 approximately, the relay's going to flip over in conjunction with the VAC switch, the VAC loading switch, which I've got as well. Here it is. In conjunction with this vacuum switch, our torque lockup will be able to work in conjunction with the brake pedal, the vacuum loading on the engine, and the speed input. Exactly what we've done and tested with this car. So now that technology, we know what we're doing with it and how to make it work exactly. And by the way, it runs like a dream on this. Very, very good way that the system works. So a clone of that system now retrofitted into Ruby. At the same time, we're working on the Crypton machines. And Bramble needs a clean. We've got 2 weeks worth of daily driving. We shouldn't be daily driving in this, but hell, it's so nice I can't help it. Let's get out on the road and pick them parts up now. Off we go for a little road trip up to CPC. We've been there before, we're going again. Straight out of Flash Gordon, here's my depth probe. Look at this bad boy, they call this the Exciter, and you can see why. Call that the Exciter. That reminds me, I've got to ring the missus. Anyway, CPC, we're here, we're suited, we're booted, the sun's out, you're in Bramble, things don't get much better. We've got, this is what we need for measuring some high voltages. What I didn't want to do is take the chance with my probe, okay? Let me just give you a little bit of a pan and tilt. Hold on, nope, not that way. Before I set off. Here's the button, this way. A little bit more of the dash. That's right. So, we didn't want to... This will allow us to measure some of the higher voltages in complete safety. I have got some high voltage probes, but they're a bit Chinatown. This is a bit more, a bit safer. And then the goodie box here from the CPC. Okay, join us then. We've got all the bits to go and do these Crypton repairs. We've got all the bits to go and do build this speed controller. You'll love that because I'll talk you through a little bit of the electronics. We're going to build a frequency to voltage converter, which basically gives a PWM signal pulse width modulation frequency. Sounds all a bit sci-fi if you're not into electronics. Now, electronics buffs, electronics experts out there, okay, bear with me. It won't all be correct, and I'll stand corrected, but you never know, electronic buffs. You might even learn from Pete at Cortina City. We've got a few tricks up our sleeve. In the meantime, let's get on the road, enjoy this little drive. I'm quite annoyed really because I won't be able to put the music on because YouTube will copyright it. That's no good. I'll have to have a section of the video where there is music, so I'll cut you out at that when it happens. Music, maestro. A very pleasant day. A very damn pleasant day. You'll hear just how beautiful the car is to drive, of course. You saw that last time.
They're easy to lose. They unnecessarily expose sensitive personal information, and they're prone to fraud or counterfeiting. And this is, I think, particularly true when the stakes are so high. And so there's, a significant desire to say, how do we take the good things about the paper-based certificates, whether used for
bugger off.
Is that right? And then at some point you say you were excluded.
Yeah, we were involved in some early preliminary discussions, but nothing substantive, and what happened in the end really was...
Bugger off. Gotta get the medium wave sorted on this. There's nothing at all.
Music.
Whoops. Woo. We can't have music. I can have FM actually.
The Bluetooth device is ready to pair. FM tuner.
I was thinking I'd have a week off before I start touring with my band again, right?
Right.
I've been here ever since, so I've had plenty of time in my pool to learn to swim. I can't believe it. 69, and I finally learned how to swim. It took me long.
So you were somebody who had a pool but couldn't swim. That is quite unusual.
No, it's drama queen.
I tell you, I mean, I always felt terrible that I couldn't swim, but I did have a traumatic experience, a couple of them actually. And, my mother, when I was a kid, she took me to the baths like everybody else, to try to learn to swim.
Drama queen Jeremy, picking up the fear factor.
That float, I just couldn't let go of it because of what happened to me before,
Well, go on. What was the traumatic experience?
Well, I was down Oxford Bay, down the beautiful Gower coast with my auntie, my uncle, and my cousin. And my cousin was a few years older than me, so she also was taller than me. And I went on this airbed, and I fell off it. And in those days, I used to have very long hair to my waist in plaits, I was only 9, right? And she saved me by pulling me out of the water by my plaits. So it was painful, but I'm ever so glad she did it,
I can see how that would be.
I fell off my yacht.
Oh, good. Well, I can see how that could be traumatizing. I've known people who, back in the day, apparently the way you taught a child to swim is you just throw them in the water and they have to get out. But that seems so cruel now.
I know. I mean, that never happened to me, thank God, But actually, that did happen to my elder brother, Lynn.
Talk about the music. Come on, Bonnie. Sing me a song. A total eclipse of the heart.
An amazing swimmer. So, you would have been there probably with me trying to travel. But I did teach my brother how to swim. I decided to learn like that. I didn't find any learn. My husband told me, my friends, you've been trying to teach me.
Wacky races. We're trying to give you content for a Friday night. It's not easy. It's not easy. This lockdown makes you can't even go and look at cars. They don't want you to go and look at. I was going to get a Capri for you, but they won't let go. They won't let me go and look at the Capri. Capri.
Was there any danger? Was there any
the thing is,
There's a South African Big Six. I need to go and look at that, really.
The nieces and nephews, 16 of them, 16 nieces and
We're
nephews.
going to talk about the
14
music. What's he on
great
about? What's Jeremy on about
nieces.
today?
And they
Usually
come
doom and gloom. Uh-oh. Hold on, we'll be right back. Here we go. Just had to take a phone call. Here we go. Time to join the M6, folks. We're heading back to the workshop. Jeremy's bigging up the fear. Go on, frighten me.
Which one I do is the breaststroke, you know.
Bloody hell. Breaststroke with Bonnie Tyler. Woo-hoo-hoo. Go on, Bonnie. Go on, my son. Go on, my son, Jeremy. And go on, my darling Bonnie. Let's get on this motorway. Let's do the business. Comfy, relaxed driving. Yeah. The way it should be.
So has you in your infinity pool.
No, it doesn't. The cover was taken 2 years ago, and it's been illustrated by a Spanish illustrator called Rectifiers, and I love it. It's a bit hard to live up to because I look so good in it. I'm very happy with it.
Well, listen, it's a delight to play. So I'm going to play the title track, "The Best Is Yet to Come," and we'll have a think about. I really want to play "Holding Out for a Hero" as well, so we'll fit them both in the next 20 minutes. Thank you, Bonnie Tyler. Lovely to talk to you.
Oh, Jeremy, I listen to you every day. You keep us all informed. It's wonderful. Thank you.
Over in Portugal. Thank you so much, Bonnie. All the best to you. Congratulations.
Thank
And here
you.
is "The Best Is Yet to Come" by the brilliant Bonnie Tyler.
I've got to listen to this.
I like to fight for the fight.
Now there's some real grime. Bramble gets some grime. Sorry that motorway clip just suddenly switched to me being back at the unit. Just the way it is. I ran out of battery power as always. We are mobile. Mobile. Yeah, I like this. I like being mobile. Look, it's fun. Okay. Guess what's open? The electronics bench is open. You're at Cortina City and you're going through a tech vid. Two things are happening at the same time. We are multitasking. Let's have a look how we got on from last week. The Crypton, our machine, restoration machine of choice is this model. I now bring it out to you. Gas analyzer down the side, down the front, sorry. Round we go. Lazy because I'm on the chair. We can look in the back of this. This tube here, this is built by Dynavision or Haya, who make scopes and who used to make diagnostic equipment in the 50s and 60s. And this was built, it's a sub-module. It was built by Haya and then given to Crypton under some kind of license deal. But it was originally made to go on a free stand. So it's got a bracket on it there. And if you look on Google Images, you'll find that there's early models of the Dynavision have this tube externally mounted on top of the cabinet like this. It looks very space age and it's very well proportioned set. The Dynavision scope was a standalone unit. And you can see here that it is that. Look, it just, with one bolt, that whole tube comes out with just one multi-plug. Look. There you go. One multi-plug. So we can test this out of the machine if we wanted. It's a totally separate module. In the back as well, the tube to one side now, you've got a sub-module here and another one there. They're all going to need attention and work to get them calibrated and working correct. We're going to make some guesses that the capacitors will be dried out. Transformer will be all right. I don't know what this is. We'll have to investigate that. The deflection gauge, that'll be fine. I won't anticipate any problems. But most likely inside here in this box, I've not opened it up yet, there'll be loads of resistors. No idea what else is going to be inside this to get these gauges working. But the first thing to get working is the scope. This is a power supply down here I've gathered. That's probably a diode tube. This is a power supply. I have to keep my eye on the screen because the camera doesn't track always where I want to go. It does well. So this is the model we're going to get going. So luckily both units, whilst one's, as I called them, baby, junior and senior. Junior has the same control box. Here it is. Junior doesn't work either. The control box is blown in that one. Tube, not sure about. Rest of the gauges, we're not sure. We've spent most of our time on this. But this one looks worse. Let's get into the back of this one and have a look at it. This video is mainly reviewing what we're going to get up to. Next week's will be more detailed. This one's took a bit of a bigger hit. So more rust and corrosion on this model. It looks like this has been in a damp environment. So this could be fun, you know, to try and get these instruments working with no schematics. And oh, I can already see a wax capacitor there. Wow, there's going to be some fun trying to get that going and refurbed. It could be done. Could be done. Well, this could just be a cosmetic sort of piece of wall art. You could do something with this. You could even change these to modern units, but you keep the original gauges. So you could retrofit electronics in here and make this work. You don't have to rely on those valves, but it'd be nice to use all the controls. It's a bit of a mission, to be fair. A fun one, but a mission nonetheless. So we've got to break it down into sections, like we did when we built the cars, okay? So we'll start by getting the scope working. At least that's the bulk of it done. These gauges, we could always work on them separately. The main thing to do is get that going. If I do get that going, then I'll probably start stripping the cabinet down. I'm going to get these aluminium plates here, these face plates, reprinted somehow. We've got someone on that. And this should ham right up okay. I believe we can get ham right. So one of the comments on YouTube, powder coat ham right is available, possibly. Let's hope so. Cleaning, stripping the cabinet won't be hard. We'll probably send it off. I don't know which bits will fit in the powder coater's cabinet. I do know a guy's got a larger powder coating cabinet, so it's not going to be a big deal. It's going to need shot blasting and dipping, re-chroming and stuff. But that bit will be fun. But I want the electronics working first, because that's all doable, the restoration of the cabinet. It's the electronics that's the question mark. And we want to get that question mark removed. So that's why we head over to the bench, where we've been doing some investigations into the unit, the control unit for the scope. So let's have a look what we've got with this control unit. Now, I'm familiar with digital electronics, mid-80s systems to early 90s digital, mainly TTL and CMOS stuff. But this one, I'm going to keep my eye on that camera. This one is all valve, okay? This control box. This controls the scope. Let's get it the right way up. What would you do with this? Well, it's very similar to a television in some respects, in that it projects a picture onto a tube, what you call a cathode ray tube. and you can control what it's seeing by turning this rotary switch here. We talked about this last week, whereby this has different functions. It basically monitors, not very much, the contact breakers. You all know about your coil on your car. You connect this to the contact breaker, or this pair. One goes to ground, one goes to the positive, and sometimes you can put it on the points as well, but you always leave the blue one connected to ground actually. This one swaps between different connections, and in a combination of those being connected and these HT leads being connected to your coil and your plug number 1, it can calculate the sequence that the engine's firing in and display it appropriately. So you turn this to check your points, your dwell angle, your plug firing voltages, whether you want to display all 4 plugs at once, one at a time, and it can do that. And that's what it is. So all that controller does is measure the firing on the engine, and you can control the position and just set the beam on the screen like you would with your old television. This is just for calibrating it so the picture looks sharp and how you want it. You've got to focus and tube brightness and stuff like that. So they're just television controls or oscilloscope CRT controls. Those, the only part that isn't is this input. And all that switch does is it just switches between looking for their low tension side or the HT sides. It just switches it. It's quite simple actually in terms of what it's looking at. It's only looking at 4 items. So here you've got the inputs coming in. Look, they've just brought it in on these cables. That's going to connect to your spark plug number 1. That's going to connect to the tower of your coil, and these connect across your contact breaker points, and with just that information it does all its work. So these signals come in from your engine here into the unit, then it's got to display them on the screen. Now, to display them on the screen in some kind of form you can understand on a line, what's called an XY graph. Let's go and look at the screen and I'll show you what I mean by that. You've got your X and Y axes like you would on any chart, and once that unit's working, the CRT tube fires up and fires a dot which moves across the screen pretty quick, so quick that it looks like a continuous line, but it isn't. It's a dot. It's an electron beam. And what I'll do to show you what I mean by that, let's go past a very mucky Bramble. Overdue a wash. Bramble's daily driving at the moment. Just getting a pen. I'm going to take you through a little bit of a tech lesson. I can hear something knocking at the door, I think there's a cat. Is there a cat? I can hear knocking at the door. Anybody? Anybody? No. I thought there might have been a pussycat there. Okay, before we go into this box and show you how it works, I'll get a piece of paper. Rather than using the whiteboard, I'm going to go overhead like this. It's easier. And talk about that scope. Now we're going to get that strobing. I don't think I can get that out for you. Oh, it's the white that does it. It's the wrong colour. Can you put up with it? I don't know if you can put up with that or not. Maybe if I use creamy coloured... hang on a sec, I've got a better idea. Isn't there some cardboard here we can use? I don't want those stripes. Does this stripe as much as that? Can we use this to demo a CRT? Maybe we can. So, not really. Okay, back to white. Right, I'm going to get you overhead, right overhead. There you go, right overhead. So, that glass tube that we just looked at, if you look at it side on, this is the sort of shape. You can see that from that red metal cone that was on it. It goes this shape. Let's get you in. Okay, it goes this shape, and it's a vacuum in there. So there's no air inside it. At the base of here, there's a little, well, you could call it a light bulb if you want, because it does glow up. They call it a heater. There's some plates in there and stuff, and what happens is, in this vacuum, this heats up rather like a light bulb was, and little electrons, it's all to do with physics, start coming off it, gets emitted by the heat. So inside here, there's little electrons, okay? And you want to fire them up this end of the tube and make them hit the face of the tube, which has got a phosphor paint on it, on the inside, or some kind of light reactive coating. What they do is they put some highly charged metal plates up this end, sometimes in a grid on the front, other times at the side, and you connect a very high voltage. I think this is right, correct me if I'm wrong, I'm trying to remember basic physics. For a while since I looked into this. Connect a very high voltage to these plates, and I'm talking thousands of volts. Turn on the little light bulb here, gets hot, heats up this metal plate, or they could come straight off the tungsten, I can't remember now, but what happens when you light this light bulb up inside, the electrons get attracted to these high voltage plates, and they shoot off down here. I think the plates might be further at the front, and they basically ram themselves or smack themselves into the phosphor, and it makes it light up. That's called a beam. So the name of the game is to get all these little electrons that are flying off the heater element here. It's just nature. A light bulb gives off these little electrons when it glows hot. When the metal glows hot here, electrons are emitted, but there's nowhere to go. They're sort of scattering around, and these high voltage plates attract them, rather like iron filings that get stuck on a magnet. But they go shooting off down here. The more voltage you get on there, the faster they go. So you need a decent amount of voltage in your tube to shoot these electrons down the tube. Now, if you didn't have any way of guiding them or focusing them, they're going to hit that phosphor paint, and you'll see it from the front. And they make it light up as they hit it with force, and they emit energy, and you get little green dots appearing. Now you need to control them, you need to make them so that they're focused, and you do that with some more plates or coils sometimes. In the case of our tube, I think it's all just contained within the tube, but on televisions you have a coil wrapped around here. This is called the neck of the tube. So when these are flying down here, if you apply electric current to some more plates, you can guide them and basically channel them up into a nice little line. It's called focusing them then. So you can get them all to follow a route. You're persuading them all to line up and make a nice dot when they strike here like this, rather than being scattered all over the place. So then you get a green dot glowing on the front, which is what you see when you first switch the scope on. And indeed with that right hand side motor scope, we did see it trying to do that, but then it went wrong. That's because the parts failed in it. But that's what you'd see. And sometimes when you turn your telly off at home in the 70s, 80s, when you had your old CRT tellies, not LCD screens, old CRT tellies, cathode ray tube, sometimes you'd see that little dot appear when you'd switch the telly off. And that's because you've turned all the power off to the controllers, and the dots are still coming off. The hot element here is still cooling down. It still manages to throw a few last minute dots, and that's why you'd see it just sort of fade out when you turn your telly off. That was just the remnants of these electrons just finishing off their little journey, and then they die out because your mains were switched off to your telly and you'd gone to bed. So you need to guide them. You need to shoot them down that tube fast. This is a vacuum inside here. There's no air in there. There could be an inert gas in there. I think they do fill it up with a gas. The bulb doesn't blow because it's like similar to a light bulb. It's a vacuum in here, so your element of your bulb or your heater here, that always runs. That glows. So if you ever look at an old television, you'll see the bottom of the neck of the tube glowing as it heats up the heater plate. So that's it. There's not much to it. All you're doing is, well, you could put another analogy in, you're shining a torch onto like the back of a curtain, and it lights up the back of the curtain. This is the same. Electrons fly down there, smack into the phosphor and make a little dot of a glow. And you use these electrical plates to guide the electrons because they're influenced by magnetic fields. So you make this electromagnetic, and you can guide these little these little electron dots, so they strike in a nice focused pattern. Then what you want to do is you want to make it sweep across the screen. So let's look at the screen from the front, the Dynavision screen from the front. You want it going across like this. Now the dot is just one dot moving, but when it goes fast, by the nature of physics, the retention of the phosphor glow and your eyes, you just see a line, but it's actually a dot. It's actually a beam. If I use my pen now, it's a beam going like this, going off there, coming back on. So it turns it off each time it gets to the end here, the beam switches off. And the magnetic plates here are doing such a sort of off and on situation that it can make it sweep like this. That dot sweeps like that because these little plates are going off and on with different electrical currents and guiding the beam in the tube, making it move inside the tube like this, putting different electrical currents on those little plates. And that's it, you're guiding it inside the tube, and that strikes the line and makes what you call a trace. Across it goes. Now, not only can you move it from left to right, the beam, you can move it up and down. And you put another set of plates on here with another electrical connection on them, so another pair. By applying power to those, when this goes magnetic, you can then make the dot move up and to the right. So you can get it going straight, apply a bit of power to it, it'll drag the electron beams up, take that power off, and it's back down flat again. So you end up making shapes. And you can make a lot of shapes. You can actually do 3D drawings almost with these, what they call vector. And that's what I used to work on, vector monitors on a game called Atari Battlezone and Atari Asteroids. And that's where I learnt my trade in the amusement arcade. So you're moving these plates. Sometimes, as I say, sometimes the coil's wrapped around the neck of the tube. But in our case, with these simple oscilloscopes, they're actually, I think anyway, I might be wrong here, but I think they're plates inside it, and they're used, as I said, to guide the way the beam moves. Now these plates go through a control box inside this unit, and that control box then connects to those HT leads into your engine, as we spoke about. Or your contact breaker points on the top of your coil. You know, and two little terminals on the top of your coil. So those cables, you hook them up to your car, put them into the Crypton, the little box, and that's the box with a rotary switch on it, so you're telling it which ones to look at. Are you going to look at the ignition leads? Are you going to look at the coil by selecting the rotor? That then has a plug on the back, which then goes to the connector on the base of the tube, as well as a high voltage line, which we'll talk about. And that sends the signals from your coil, your engine, your contact breaker points, through a little bit of a breakdown box, onto those plates, and guides that beam to make that shape. So that's it. It's just making a shape with the beam, and the fact that it's phosphor glows. So when the little beam hits that phosphor paint, you see it as a glow. Colour tellies are a bit more complicated, but that's a simple CRT tube that's used in an oscilloscope. A rough explanation. It's the best I can do. There are more detailed explanations available, but that's my interpretation of it. I'm drawing on my memory now, so I could have forgotten stuff, but I'm sure if you think about it, it does make sense, you know. There's another analogy you could do, which if it didn't quite get your head around that, apologies if I didn't explain it well, and is a crazy analogy, I suppose, but it would work. Get a ramp, okay, like a ruler or a ramp, put it on your bench and have it tilting up, and then put a steel ball bearing on one end. Let go of the ball bearing and it runs downhill. That ball bearing could be those electrons, if we were going to use this analogy, and a magnet on either side. As you let the ball bearing run down there and you put the magnet nearer to the ruler or the ramp, the ball bearing will head towards the magnet for a bit. If you quickly pull the magnet away, it'll carry on rolling, so you can influence the ball bearing rolling down the ruler or the ramp by putting magnets on the side. You can imagine it would work. You could try it. We're not going to try it at home, I know, but I'm just saying you could prove it. If I got on this bench now and put a ball bearing on it and rolled it on the bench, but I had a magnet near it, as that ball bearing started to roll, it'd start coming towards that magnet, wouldn't it? That's quite easy to get your head around. Well, it's the same in here, but instead of ball bearings, the little electrons and the magnets are electrically controlled. So you're just making that little electron that's getting chucked off this hot plate here and land in the right place that you want, and it's all about controlling that. So that is it. There's a lot more to it because you've got time base, you've got sweep patterns and all sorts of stuff, but very crudely that's what's happening. It's the best I can do. I'm sorry about that. I couldn't get it any clearer. So that's that tube. That is what we've got. There's your phosphor is on the front. It's not that yellow actually. It's actually a grey colour. So that is that tube, and that is its control box there. Forget everything else that you can see on the machine and just think about that just for now. Otherwise it gets too much. So here's the control box. And how's it going to do it? Well, remember when I said it needs a really high voltage up this end to accelerate the electrons and make them really fly, equivalent to you getting that ball bearing on that ramp and tilting the ramp up so the ball bearing goes flying downhill. Same here, it needs tons and tons of high voltage at this end to shoot them down. They're going to get attracted to it. It's a positive charge and they're going to get attracted to it. So what you first got to do is get your high voltage up and running and get your low voltage on your heater up and running. You need both those going to get your beam. Now they do that with a transformer here. So this is just your normal mains transformer shape. It's resin coated, it's resin dipped, this one actually. It's dipped in the whole thing's dipped in a resin. That transformer there, it runs a couple of things on the board, not much. Runs what's called the valve heaters, the tube heaters, the low voltage power and the high voltage power. Now we've got to make something like at least at 1000 volts. We need at least that. So it has to make that because these tubes need that to get that up to speed. If the lower voltage, if it's too low a voltage, these don't strike it fast enough and you get a very dim dot. And you can tell when your power supply is starting to fail because the dot starts dimming out. The power supply is done. This is early days before they used diodes a lot. Well, diodes were around, but they used tubes as the diodes. I'm going to tell you what diodes are in a sec. I'll just get a tube. Here's a tube. By the way, if I make mistakes here, I'm only learning this as I go. So I'm open for correction and I'm open for suggestions and help on this, by the way. Please, I've never worked on this kind of kit. I am chucked in at the deep end. I'm going off my memory from physics about the tube, the CRT, and I'm going off what I can decipher here off the internet and everything else. There are no diagrams for this, so we've no idea what we've got. Nothing for it, just what we see. So I'm going to move the lamp in front of this just to give you a better light. That's the whole point. We're going to break it down again. Talk about breaking things down into sections so that you can digest it better. Power supply area here, low voltage power supply area here, high voltage power supply is here. And they do, on this transformer here, there's different outputs. So let's say you've got your USB charger at home, that's 5 volts. When you plug it in to charge your phone up, you've got one cable coming out of they're actually not power packs anymore, they're actually not transformers anymore, the PWMs or the switch mode power packs. But the old days you had that heavier, remember those heavier AC adapters into the wall, one wire coming out? Well, this one's like that, but it's got 3 or 4 different types of voltages coming out. You could have your 12 volts, you could have your 6. So this has got 6, 300 minus and 300 plus AC, or AC 300. All sorts of different, what they call tappings off the transformer windings, which you can use to create different levels of power supply. It might have a little 6 volt bulb on the front you needed to light up, so you could come in off the 6 volt feed off the transformer. So it's got about 4 different voltage outputs on this, 3 or 4. One of them is the high voltage output. And this tube needs to be DC mains, DC rectified. Coming into your transformer is what you call alternating current, and that's a sine wave shape. We need direct current to drive the high voltage, and that's where these valves come in. These valves here are called rectifiers. They fit in these sockets, and they convert an alternating current into a direct current. That then feeds into these capacitors. They're like energy tanks, these, and they take the rough, choppy voltage that's coming out and they smooth it out. They're like little batteries, and the way that they work, they store charge. They eventually dissipate, so there's not a battery that would last long, but they do hold charge. And this is where you've got to start being careful, because you're talking about 1,000 volts across in certain areas. We don't know where those areas are. We can only go off the clues that we see. And also, we've got even more clues, because this isn't really rocket science. It's just a very simple scope, and it's already been done. There's nothing new under the sun here. Power pack, high voltage power, low voltage power, a switch here to switch the inputs to wherever you want to do your points, just one spark plug, all 4 spark plugs, whatever. So that's your input selector. This at the top here is what makes the beam sweep across. It's what's called time base. It's a little clock type situation, and it makes the beam do that sweep. So it's controlling those plates I talked about, which make the beam move. So that's the sweep, I think. Spinning it round, there's another board which I think handles the inputs, and depending on where that switch is selected, it will attenuate or reduce the voltage or switch the voltage for the input so that it's suited for whether it's your coil, your contact breaker points or whatever. So that's a kind of like input control, I think. There's one valve on there. This might be the opposite way round, where this is creates the sweep pattern, and the board on the other side is the input, but I doubt it, because I'm looking here and I'm seeing 2 valves here. I'm going to move the lamp. I'm seeing 2 valves here. Push back. Better for you. 2 valves there. Okay, and they, I think, control the beam going from left to right and the beam going up and down. I reckon they're like transistors there. That's a guess. Could be wrong. So I think these perhaps are controlling the beam, which means that board at the bottom is something to do with the beam. And indeed, I can see a variable resistor here, like a volume control knob, if you will, which could well be to do with fine-tuning perhaps the focus, or fine-tuning the brightness, or whatever it is. It's set, and you can adjust it, but it's factory set and marked with some paint. I think this is the time base that creates the circuit to make those plates move, thereby moving the beam. So that's giving you that sweepy pattern. The up and down bit, to a degree, is controlled by your input of the voltage of your spark and stuff like that, but that'll still need to switch this so that it can switch that beam, because you remember you're talking about switching high voltages. I think that you use high voltage to control the plates there, and also high voltage to make the beams, make the electrons slam into the phosphor. But I'm not so sure if this is much higher voltage, like this is like 1,000 or 2,000 volts up here to get them really flying, and that the 600 volts is used to control the deflection plates. I don't know. I'm still trying to reverse engineer it, how it works. I've also gone online looking at scopes. So control your inputs here so we know what we're looking at on the engine itself. Make those inputs move around, make that dot move around where you want it on the screen, and then these controls at the front are just to fine-tune the setup. So indeed it says tube brightness, tube focus, and then some voltage adjustments there, vertical and horizontal adjustments, that'll be your width and stuff. A test button for kilovolt test button, that'll be for calibrating, so that you can work out your spark plug calibration, I think, or it could be something to do with just checking the set itself and nothing to do with the engine. But I'm not sure that's to calibrate your spark plug voltage of your spark plug, because different engines, I think there was a 15k range. Let's just have a look. I think there was a 15k range. Yes, there is 15k range, look, and 30k range. If you had a more powerful coil, you'd flip that switch and then you wouldn't go off the scale. So if I've got it on 15 and my car's chucking out 30,000 volts, that's going to go right off there. Consequently, conversely, if it's a low voltage coil, you need to be on the smaller screen, because this would be too compressed. You wouldn't get as much detail. Your detail would be lost as it squished it down. So this, you can tell the voltage adjustment you can set the voltage adjustment on the rotary switch at the front, so that's to tune it into different engine power. Example, Jaguar's coils might fire a lot higher than Ford Cortina coils, so you flick it to get the right range and you tune yourself in. This normally has a blanking plate on. That's normally all set and done, then you leave it and you put the plate over it. Perhaps the Crypton man would do that for you. I would probably recommend referring to the book. So ignore them controls, you've really only got that. So the user would be able to do the horizontal spread, it's called. That's the width, and the hold to stop it jumping all over the place. There's not really much to it. I'll go over it one more time. There's a lot to take in. Push back into the light. Go over it one more time. In fact, I'll tell you what I'll do. I'll lay it down now to get a different angle, just to vary the footage, because it can get a bit boring at one angle, can't it? Let's go back through that again. Very quickly, I won't bore you with it anymore. Remember, you've got a little heater bulb at the very bottom of the tube. Gets dead hot, heats up a metal plate. It's probably a certain type of metal as well. And that, by physics, it starts emitting electrons, little tiny electrical charges. You have a very high voltage up this end that attracts those at very high speed, and they smack into phosphor on the glass and make it glow by the impact. Like chucking a stone in a pond, you get a splash. Same here. But you want to control them so they don't just scatter all over the screen. You want them in a nice focused pattern so that you can display information on your screen. And that's what we get. We get these electronics to control that. We control what we're looking at, perhaps with this board if we're right. We might be looking at the contact breaker points doing this. We might be at a spark on your plug number 1 doing that. In which case you'd turn that selector switch. It would route the cables, these cables that are connected to your engine. Look, there they are again. I showed you them before. It'll route those cables into different points on here. Drop the voltage down a little bit, then pop it into this board. And these little tubes here are like switches. And they'll switch the beam plates in a certain sequence that makes that dot become legible to you, i.e. from left to right across the screen and up and down depending on your spark voltage. It's always going to go left and right on its own, but it'll stay still till you put your spark plug on it and it picks up a spark and it shows that as a line. So when your engine sparks, you get these like little spikes, like sawtooth spikes, and that's it's a spark. So you get that shape, and that's why you get that shape, because it's always scanning from left to right. And you can, the genius about this, these scopes for engines, is that they can what's called parade the display, and that is they show all 4 spark plugs, and you only have to have 1 lead on. It's because it picks it up off the king lead, and it works out the timing off plug 1, then just assumes that as soon as plug 1 fires, then the next 3 pulses must be 2, 3 and 4 for a 4-cylinder engine. You can go up to 8 cylinders, again depending on how you set the switches, and that's why you've got some switches up on the front. Let's have a look for the cylinder switches. Yes, here we are, look, 2, 4, 6, 8 cylinder. So that gauge there is going to have to feed back to the control box, and it does on this yellow cable. I'll show you what I mean. So let's remember that controller switch there. And there's a voltage switch. This may be applicable to the scope, because I don't think the scope's got the scope's got the option on the control box to have the amount of cylinders. No, it hasn't. So this is going to need to be told by them switches on the panel what engine it's looking at, and that's what this second plug does. So this second plug comes in, depending on how you've got your cylinders set on the scope panel, will change the timing of that dot going left and right, and the up part of it, the spike part of it, and tell it, well, count 3 because you're on a 4-cylinder engine after plug 1, count 5 after for a 6-cylinder after plug 1. So that's all they'll do, and they'll do that with various little electronic components. So this is needing some info from the control switch, so we may have to test it with that plugged in, so we might not get the readings that we're expecting, although we certainly should be able to get a sweep. It won't need that to just get that beam to sweep like that. That's not controlled by this, I don't think. Again, without the schematic, very difficult for me to reverse engineer just yet. Love to speak to someone that worked and built these. 1960, early I would have thought, this is 62, early I would have thought anyone who worked on these, or anyone wants to add their technical knowledge as to whether I've missed something, got it wrong, or what. I'll run through again what I think it is to correct me if you think I'm wrong. Input transformer, multi-tappings on it. Low voltage DC rectified power here. High voltage DC rectified there for the tube grid. Possibly the control input board. And at the back, that board at the back, the deflection plates. Am I right? Then these just simple bog standard focus controls, horizontal controls. I think that's what it is. Now the good thing is, we'll move away from the techie stuff now, or take the pressure off at least. The good thing is that it's very, very simple. Nothing in here is complicated. Despite what some people might think, it isn't. There's actually nothing to it. The valves themselves, I've got some new ones, are quite easy to understand. These radio valves here are just rectifiers. But I could have a whole nother lesson on valves. We're not going to do that. But the valves are responsible for controlling the high voltage. Indeed, you can tell what they are because of EY. That means diode. Okay. Two of them diodes are responsible for making the high voltage power supply. So if we're not getting high voltage on these, what I call cans, the capacitors, we know something's not quite right. We can check everything. Now, I've already began to check the power supply. We're going to start by checking the power supply. Forget the beams pattern sweep at the moment. We just want to get high voltage going because that's what was failing on it. And I've found this is short circuit. This capacitor here is short circuit. That's one of the high voltage capacitors, and you can tell it is because it says 3.5 kilovolts on it. So you know that that area is for the high voltage. It has to be, so you wouldn't have these types. This has gone, it's burnt, and you can see that it's buckled and it's beginning to go like a balloon, and eventually these can pop and chuck out a bit of fumes and stuff and they can go crazy. But they're well known for going short, simply because of the lifespan of them. They haven't got a long lifespan before the chemicals inside break down. And the way that they work is these store power. If I was to put a battery on this, 12 volt car battery on either side, it would charge up with 12 volts. And it would stay charged with 12 volts for a long time. But it wouldn't, you know, you get, the bigger the can, the more power you get. But they're just like batteries in a way. They behave a little bit different, but it's a bit the best analogy I can think of. But they smooth out the power coming out of here because it's very choppy, the power coming out of the transformer. It's very, very rough, and these sort of act as little reservoirs and store it nicely so that it's smooth power. If you don't have smooth power, that little electron beam I'm telling you about will be wobbling all over the place, and you're going to see it. Everything needs to be smooth to get that beam nice and smooth, and everything needs to be the right voltage as well to get those electrons to go flying across inside that tube. So you need good high voltage power, and that's what that does. You need a little bit of low voltage assistance for that little heat I was telling you about, and also for these tubes, by the way that they work, these need to get hot too, and that's why you see these tubes glowing, because these have a little light filament in them too that glows, and that helps the action of the tube. I don't want to talk about tubes today. I can if you want, but I don't really want to talk about tubes, but except to say that they need some power to them to wake them up, to get warming up, and then they can get on and do their job. In this case, it's a diode. It turns the AC power into DC so that you can get this high voltage DC power. High voltage AC power is no use. The electrons aren't going to get excited by that. They need DC high voltage up there. Right, we know we switch the inputs with that switch. It's a no-brainer. We know there the television control is simple. There isn't anything else really. The only hardest bit would be trying to decipher what's going into this plug, but it might just be easier to just plug it into the machine when we get that sweep pattern. We've got no sweep pattern at the moment because both valves were blown. Here's one that was blown out of this set. You can see it's blown, it's gone milky white, and it's got a crack in it as well at the bottom. I think that this capacitor went short and then blew this valve. Now, we did switch this set on, so we could have blown that valve by not taking that cap out of the circuit, and that's the problem. I did warm them up, but really what you're supposed to do, what I didn't do, but don't worry, we've not done any harm, is really you're supposed to not even power anything like this up at all and check for shorts on your caps. In fact, just take your caps out and just replace them. These just can't survive that amount of time. It doesn't matter how hopeful you want to be. If they've not gone now, they will go. So you just got to find them online. There's a site called Maize, which I found some on there, and I was lucky that the numbers are on them, so we can read them off, go on the internet and order them and replace them. Now, I pinched this one from the other set. That's why you can see that it's not missing. You might have spotted I've took that out, but it's still got one in. That's been nicked out of the other set, but that's also knackered. So the other set's done exactly the same thing. And indeed, I went into the other set, opened it up, and that valve had blown. So someone's blown it up before I've blown that one up, because it never worked. I mean, I'd powered them both up, and they're both dead. I've done some damage, and then someone else has done some damage too. Possibly when it was on eBay, they've plugged it in to see if it lit up. There's no way you're going to get around that. So replace all the capacitors, put 2 new valves in it, and then we should get our thousands of volts working. We should hear it as well, and it should be running. And then we can start looking further up. Now, all these capacitors, even the small ones, are no good. We've got to replace everything. And some of these resistors I noticed, I took that one out of circuit just as a spot check. You can check them in circuit, but sometimes it's nice just to see. All of these have drifted. They're all different values. These are like little resistors, little taps in the water pipe, if you will, that restrict the power going through. They're all different values. And these are looking way out of tolerance. Every single one of them looks out of tolerance. In fact, they look so out of tolerance that I was wondering if I was reading the colours right. I do know my colours. Example, you've got this one's 24K, 240K at the top, red, yellow. Hang on a sec, red, yellow. These are just code letters here. These colours on the resistors just tell you the amount of resistance that it's giving. So red is always 2, yellow's 4. So you do it on a chart, you go 2, and then 4 is the next number, and then the last number is the multiplier. In this case, you multiply by 4 zeros. So you've got a 2, a 4 with 4 zeros behind it, which is 240K. So that should read 240K, but it doesn't. It's nowhere near. It's something like 130K. The same happened on this one, so much I couldn't believe it that I snipped it to test it, to make sure the circuit wasn't creating a false reading. So I tested it out of circuit, and that was just like 100K out on whatever it was. You know, this is 50 grey to 52K, 3 zeros at the end. So that's 52K. It was nowhere near. So all them resistors, I think, are gone as well. I don't know why, because resistors, usually it's the high mega ohm ones that go, not the low end ones, but it seems that everything's gone, and that's dead. That's even, that resistor there on that cap here on the high voltage supply is completely open circuit. There's not even anything on it. It's not reading nothing. That's brown, green, yellow. So that's 1. It's green 5 or is blue 5. It's something, I think blue 6. I always have to have my chart. I remember the first few. Let's say it isn't. It's 160K, whatever it is. It's gone. It's open circuit. So that's gone. So loads of bits have gone. There's just no point trying to just like fix one bit and shove it back in the machine, because everything's just going to fail. We really got to just strip everything out. So that's where we're at with that control box. It's interesting. I tell you what, someone who does scope repairs, someone who does television repairs, and they've done that as a job, it's not my job, would get into that and say, yeah, they'll be gone, they'd easy do it. Because it ain't rocket science. There's actually not much to it. The oscilloscope is such a simple instrument in its base form that there really is nothing for us to seriously worry about. It's only a question of getting the parts. Now we've kitted up ready to test it when it does start to fire up, especially the high voltages. What you don't want to be doing with those high voltages is you don't want to be electrocuting yourself. And your normal meter as well won't read high voltages anyway. This one probably only go up to 600 volts. What do we go up to? Oh, this one goes up to 1,000 volts. This one's a little bit better. This nice meter here, this 10x one. But 1,000 volts, well, you got 2,000 volts, you know. And also, do you want to be gripping these leads with 1,000 volts on? Because I bet you sometimes you could get them tracking through. So that's why we get this this high voltage probe, which looks like something it's either out of a Flash Gordon movie or an Ann Summers shop. Take your pick, and anyone that gets in trouble and gives us a thumbs down has to inspect the inspector probe. So, this probe It's one of the ones we used to use. Well, this not exact model. I used a similar one. I had to leave it at work when I left the company. But this, we used to touch this on to the high voltage parts, and you were completely safe because you were nowhere near. It gave you confidence to test. So that would on your meter reduces it by a factor of 100 or 10, depending. So your meter could then display the high voltages without having to get special high voltage meters, which were very expensive. So that's our high voltage probe, or sex toy, depending on how you want to look at it. Although really, doesn't bear thinking about. So that's that. We also need to. This can kill you. All right, this can kill you. So if I touch those caps like that, I'm dead. It'll attempt to stop my heart. That's what will happen, and I'll pass out. So I'll hit this. The current will strike through. The direct current at that voltage will travel straight through my arm. And if I'm not sat right, there is a certain position you should have your right arm if you're doing this, and so that you don't get the path across your heart. What you don't want to do is the electricity goes across the path of your heart, and because that stops it. Now it won't kill. If there's someone with you, they can get your heart going again. But if you're on your own, then you're dead. So that's it. That's why you can't take any chances with this kind of equipment. No chance. This open chassis like this is a death trap. And that is actually no exaggeration. It will. That's a suicide, if you want. That is a simple suicide. Bang and you're dead. That's it. You could survive. People get struck by lightning and survive. But I wouldn't like to be trying it. So what you do, you're never going to be able to stop that high voltage. You're always going to be measuring it with insulated equipment. Also, what you don't want to do is be across direct mains anyway when you're working on this kind of stuff. So this transformer over here, you put mains in, right? And it gives mains out, but it's not connected to the mains. It's a transformer. So inside here is this big, this black stuff. It's actually copper behind that's tape, like a high temperature tape here. But behind that is copper windings. And what it does, I'll just show you how the transformer works so you know that we're not connected to the mains anymore. Look, with this transformer, this safety transformer stops us from getting some real serious high current belts. So the copper wire is wound round like this loads and loads and loads of times. Imagine yourself getting a piece of string, or a piece of wire indeed, and wrapping it around this pen so you get a coil like that. Well, instead of wrapping it around a pen, they wrap it around these plates of metal like this. They're this shape, look. See that? They're laminated. Square wafers of metal laid, sandwiched together, and then bolted. So you've got tons and tons of square metal plates, and you wrap your cable around them like this, look. Loads of times. And the ratio of the wraps dictates the voltage. So there's a direct relationship between what's called the turns or the windings on what voltage goes in and what voltage comes out. That's a transformer, so you can make anything. It's always 240 mains if you're connecting to mains, that is, in the UK at least. And out, you can get all of any voltage you want out of there. You can go up, down, and in this case, in this case at least, that's the same. Look, you can see the wafers there, the metal wafer. Oh, sorry, I wasn't pointing you up. In this case, you can see the wafers there. It's got multiple wires coming out on the output side. It doesn't have on the input side because it's just mains in. But you can take different points in the wire and bring off different voltages. In fact, what they do is they multi-wind it. You actually have a separate set of windings within the same unit, multi-tapped. But that's a transformer. That's all a transformer does. So this big beast over here, there's no electrical connection to the mains. Look, you've got metal in the way. It's magnetic force that does it. So when you plug this into the mains here, all these coils of wire, they pass a current through them and they make magnetic fields. Remember, we talked about the magnetic fields that guide the electron beam here, more magnetic. And the magnetic fields induce eddy currents into the wafers, the metal, and this side picks it up and it turns it into electric. So the magnetic forces go from one side through the metal and induce themselves into the wires here, and it creates electricity on this side. So there's no connection to the mains. There may be an indirect way if you're following your earth through, because sometimes earth wires are tied into the neutral point. You've got to be careful about that, because sometimes you're not truly isolated. So that's something I need to look at. I seem to recall that from tech days, about the earth here. We've got to be careful with the way that the earth works. I'll double check on that. But that transformer is another level of safety for us. So we've got that as a level of safety. We've got this high voltage probe which insulates me really well. And indeed, if you see these circles on it, it looks Flash Gordon. Look on your high voltage telephone lines. Not telephone lines, your pylons, and you see these. So these will have something to do with stopping either flashes. The reason that it's circular, there'll be a physical reason for that. I don't know what it is. Definitely be a reason for that. Looks like Flash Gordon's ray gun, doesn't it? So that's another level of protection. We've got an RCD breaker as well on the fuse board. That's going to help. We've also got what's called a Variac. It's another handy piece of kit, which helps us again, safety and through setting it up. Now this one I got new off eBay, like a quarter the price. It was an absolute bargain. These are normally 700 quid for Regavolt. I didn't pay anything like that for it. It was a bargain. Brand new Regavolt. So we can, what this does is, this varies the voltage. If you've got 240 on your mains coming into the transformer here, I can drop it down to say 110. And the advantage of that is when we're rebuilding something as old as this, is you want to gradually bring the power up. It won't do it any harm, and let things gently come up, just so you can see if anything does suddenly explode. Then if you suddenly just connect it to the mains and I've missed something or something's short, it's pop and gone. With this, you get that early warning chance just to see it slowly wake up. And indeed, we should see the screen slowly come to life and the beam slowly come on as I wind the power up. So that's a way of just gently introducing power in, and you can run it at lower levels of power. We can run it at 120 volts if we want, or run it at 150 volts and slowly bring it up to power. A handy little unit to have for testing stuff, especially old television and things. So you really do need to get yourself set up. There's no way you can just come in quick and just jump into this. It's too dangerous. It's all right if it was electronics, an old radio, transistor radio, or digital radio, something like that, where you've just got AC adapters running it. This kind of stuff is serious. And because it's an industrial piece of kit, really, there's no warnings. There's not one mains sticker and one mains warning anywhere. Nothing. Like nowadays, there'd be risk of death stickers all over it. There'd be this, do not use without authorized. But again, they wouldn't make this now. But, if something as dangerous as that, with no warning at all, return to service agent or anything, nothing. So this is it. This is what I'm saying. We cannot take any chances. I'm not ready for leaving the planet yet. So, I want to do that. There may even be some safety features which I've not mentioned. I don't know. But I just don't want to leave the planet just yet, if that's all right with you. Hopefully, that's explained some stuff about the transformer being isolated, about the way those electrons fly around there and hit that phosphor paint and make that glowy dot on the screen that you see. So whenever you look at an old telly now, you're going to think, I remember Pete saying about that electron beam hitting there, and then plates making it sweep across, then turning off, then coming back, off, back, called a sweep. So there we go, sweep that beam, then go so quick that it looks like a continuous line. And then as it goes in, it connects to your car engine and it detects the pulse of your ignition plug sparking. It reads that and flies up in the air. But as it's flying up in the air, it's also still going to the right, so you get like a ramp. Then it quickly drops off, and the way that shape is created gives you all the different patterns. Let's have a look at those patterns now, so I can tell you a little bit more what I mean. Here's the patterns in the book, because they show you how to interpret the patterns, so you can establish what type of problem that you've got. Look here, here's the patterns. Here's our scope. There's our beam going across, look, all the way. And as it goes across, it measures things in what's called the time base. So that's the time base. That could be 1 second. From there to there could be a second. You can change the speed which that beam flies across on the scope controls. And indeed on here they'll have done it by doing the various cylinders and stuff like that. So we don't need to worry about exactly how they've done it, but you can change the time base. And they'll have set it for what suits a car engine. Look at these different patterns that we've got. And then it tells you how to interpret the patterns to look for, in this case, distributor dwell overlap or coil polarity. A reversed coil gives an inverted reading because it draws it down. Remember, I talked about that beam going left and right and up and down. A positive on one of those plates will pull it up, and a negative will pull the other plate down and make that beam fall down as it's getting shot across. So look, connecting your coil up wrong can show up on the electron trace. So that's how you can start to spot things. Here it's showing an unsatisfactory coil windings. Excuse me, I've got a dust allergy at the moment. I've not got a cold. I've got some crazy dust allergy. I don't know what it is. Anyway, I'll look into that. It's not hay fever because it's the wrong time of the year. It's something to do with dust. All these different patterns. Here's a 6-cylinder engine. I think it is. Sparking plugs, yeah. I don't know why they've done those numbers like that. They could be referring to, oh, they're referring to different types of fault. I don't know why they haven't done them sequentially though. So that's how it all works on the scope patterns. They tell you how to read what you're seeing on that. And that is that subsection. Spark plug patterns, look. For example, it says here, circuit with series residual or partially fouled plug, series resistor or partially fouled plug, showing that one of the sparks is weak. Remember we talked about that kilovolt scale there, look. Shorted plug or plug lead grounded, you're not even getting a spark on 5, shows up on the scope. So this is still used today. This type of technology is still used today. You can still buy these items, not motor scopes, but you can get modern digital equivalents of them. Put that in there for now. So that's how that is. So we now can't go any further on the scope because I haven't got the parts to keep on going. I've got some of the parts. Look, here's some of the new resistors that I've ordered and have arrived. Well, we picked them up, didn't we? You saw me on the motorway at CPC. They can go in there. Different values, different areas. But we haven't got enough stuff. We've got some stuff, we haven't got the caps. So I can't start doing any more with this. All we've done is used our time again to build up stockpile of things that we need. So I'm going to put this to one side now and tell you about something else technical. That will hold for next week's video. So say goodbye to that tech lesson. And sorry it's all techie tonight. I'll lose a lot of people because of this, I suppose. But I like doing it. We're now switching to our friendly Vero board. What's Vero board? You solder all little electronic components on Vero board and make your own little mini circuit. What circuit are we making? Well, I've drawn it out already and here it is. Hopefully you can see that quite nicely actually. This, do you remember Project Ruby? Do you remember Bramble? And our lovely torque converter lockup system, activated by speed, switched off by the brake pedal, switched off by the vacuum pressure if it's not satisfactory, but on a timer so you don't get any chatter. On the vacuum switches can click like this, so we've built a timer to dampen that down and make the relay come in just on 20-second cycles so you can't flip it or blip it. Remember that? It's covered on some of the other videos. Torque converter lockup on the A4 box. Controlled by a speed sensor coming off the prop shaft, which is used for cruise control as well. That's built into the gearbox when I put the new gearbox in. This is a later box out of a Granada. It's got the speed output sensor on it, so I used it for cruise control. It's also got a mechanical speedo cable, so it's a dual tail shaft output. One side's got the speed transducer, the other side's got the physical speedo cable. So your speedo still works on your dash, you don't need a digital one. Yet you've got an output, square wave output, to run your cruise control, because this has got cruise control, as you well know. And we get it to run the speed sensor switch, which we built to turn on the lock converter when we're over 40 miles an hour. Ruby hasn't got that. Ruby's comes on with the cruise control only. I want this system on Bramble so good that I'm building myself a speed activated relay for Project Ruby to retrofit in. Here it is, the first stage of it anyway. This is just the speed controller. There's other timer sections we need to add to stop that vacuum switch chatter. But this is a circuit for speed control. And if you've not done circuit designs, this is going to look a bit strange. But it actually, again, is not. You do that same principle I just talked about. You break it down into sections. This can be split straight down the middle into two completely different circuits. So you could just look at this side. It's dead easy how this works. You've got your speed signal comes in here. I show that as a square wave because these are little 12-volt pulses. Every time that speedo sensor on the back of the gearbox turns, or in fact it does it more than one revolution, but let's just assume it's a pulse every time it turns around. 12 volts, 12 volts, 12 volts. As you get faster, 12, 12, 12, 12, 12, 12, wow, like that, really quick. Pulses coming off your speed sensor. This circuit measures the pulses, okay? Has to go into this little transistor here to switch it. That's just the way to invert these signals, because it doesn't want to look at a positive, it wants to look at a negative. This little timer chip, they're off the shelf, little timer chips, and this slows everything down and converts it to a voltage. So the faster the pulses come into this little chip here, the more voltage it puts out on the other side of the chip. So it's called frequency to voltage conversion. So you're just getting your pulses. The faster you get those pulses, the more voltage this goes out. Now, it's not going to be 0 to 12, but for example, I'll say that it is. It doesn't actually do 0 to 12, but let's say no pulses is 0 volts. 50 pulses a second is 6 volts. So the faster you turn your gearbox or speed or drive the car, the faster the pulses go into this. This counts them and turns them into a voltage. The voltage comes out the other side. So if you used to connect a light bulb here, or an LED or a voltmeter, as you got faster, your voltmeter would be going up. So that's all that does. It's a 555. You can configure them to do all sorts. In this case, we've set it as a called a monostable configuration, and it can be used. It's a great little side effect of the chip. You can use it as a speed to voltage conversion chip. So forget what's inside the chip. It's not important. These little parts are just to calibrate it up, because some speed sensors are different. You need to match the chip to what speed sensor you've got. Most of them will be the same, but this circuit can be used for counting stuff that runs a lot quicker. The speed of a windmill blade on a wind farm, the speed of RPM on a specialist drill, whatever, loads of different things. But in the case we've got here, I'm using it for car 12-volt input. So that voltage then comes out, and then there's another chip here, they call it a 741 comparator, and that you set a set voltage to look at with a little adjustment screw. These here are what's called variable resistors, a little tiny little adjustment screws. We call them pots. I'll show you a pot, not the pot you want to smoke, unfortunately, although I get too paranoid on pots, so I don't smoke it because it makes me totally paranoid. Where is a pot? Here's a pot, a trim pot here, and you turn the little screw on it with a little miniature watchmaker screwdriver, and that's going to give us our adjustment when the speed relay clicks in. We're going to fine tune it so the speed relay clicks in at, say, 40 mile an hour. That's how it's done. So we told you that the faster I go, the more voltage comes out of that chip, because that's the way that it's set. Then we just need to compare the voltage with a set level. So that little pot is represented by this diagram here. I trim it, and this chip looks at the set level, so I might trim it to 2 volts. And then it'll look at the difference between this and 2 volts, because it always needs something to compare it to. That's why that's called a comparator. It's got these comparative inputs. So you're going to set a reference voltage, which is done. In fact, I've not marked that zener up. I'm going to probably put, this could be, well, 4.7 should suffice, because that's about just under 1/3 of our power input. 4.7Z zener, right? This is a voltage reference. I'm not going to go into electronics because it's too long a video, and I'm just going to alienate people, and you're going to zone out on me. I trim this little pot here, and there's another one there for the upper range. That's called the hysteresis, the switching point between the two. So we get 2 switching points on at on at 60. Back off at 40. If you just had it on at 60, it's so accurate this, that as I went 60.59 or whatever, it would click out. Then as I go 60.6, so in other words, the minutest mile an hour change would have this relay going click, 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 click. Is my click, click impression any good? Click, 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 click. As you're hovering around it, it's no good. You need hysteresis. Same as you've got in your house thermostat on your wall of your house. That will come on at 21 degrees, but it'll go off at probably 20. It's got a 1 degree hysteresis in it. If it didn't have, your room stat would be going click, 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 click all the time. So hysteresis is that switching tolerance, upper and lower limits. You've got to have it on a speed controller because we're drifting faster and slower in Ruby. We don't want it clicking. We just want it within 10 mile an hour. So these little trim pots, you turn them with a screwdriver and it alters the resistance on this part component, which means this comparator looks for different values and it will set what's called a hysteresis. Indeed, you need that diode to run it at the top. There's a little transistor there and the relays at the side here. So that's the switched output. You don't need to look at that. That's your comparator. That's your frequency to voltage. So that's how a circuit, even though I've said that now, it'll probably still have to sink in if you've not done electronics. Don't let me, I'm not patronising anybody there. Sorry about that. I don't mean to do that. But signal comes in. This little chip can count the pulses depending how you set the calibration. We need to set it at about 50 hertz. 50 times a second is what they run at. I've had the scope on them speed sensors. Calibrate it in the rough ballpark so it can see the signal. You need it to get it to see the signal because this can see stuff going at 1,000,000 times a second. Maybe not 1,000,000, but it can go at least 100,000 times a second. That can count 100 hertz. It's very accurate. A very durable chip. But it would miss this then, so we need to roughly calibrate the chip so that it can see the type of input we're using or the frequency of the input. And that's what these components do. The little trimmer at the top, a 1 meg trim pot. We set that. The faster we turn the engine, the gearbox output shaft, the more voltage comes out of pin 3 of the chip. So it goes from 0 volts, then it goes 1.2, then it goes 3.3, then it goes 4.4, and I might be at 90 mile an hour now, and I might get 6 volts out of it, depending on how it's calibrated. This then looks at that 6 volts, compares it to a set known level, which I've predetermined, and it says, right, it's this much difference, I'm going to switch the relay on. So it then energizes a little transistor here, which switches the relay on, and that relay is what switches on the torque converter lockup via the brake switch, because you have to have it coming off with a brake switch. And also, I don't want the torque converter locked on when it's got the wrong vacuum loading on the engine. I want it to drop out, and that's why I have to fit a little switch here, which I'm about to get out. I think I showed you this earlier on. This switch will also block the signal. So this is just part one of it. There's another section of it there. Also, when this switch triggers, this can also chatter. You can get the vacuum on this to just dance the switch a bit. So if I'm hovering on my foot on the car with the vac, it can be just at the point where this switches, and this switch will go click, 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 click. We don't want that making the lock converter plates going like this. So you have to damp it with a timer circuit. So we fit a timer circuit to this, so every time I activate it, you can't do anything with it for 10 seconds until it turns back off. It's called damping or delay, whatever you want to do. That circuit tags on top. It's a dead easy circuit, the delay circuit. Nothing like this, it's just a transistor and a capacitor. It's easy. So that is it. Now I know not everyone does electronics, but that is what we're going to build. Electronics is quite fun once you get into it. It's not as hard as it looks. In fact, it might not look hard. Again, I don't want to patronise anyone. But I had people saying, oh my God, it's like voodoo and stuff. And then other people are way ahead of me. This is child's play. Some people just way ahead of me and can do this times 50. This to me, well, that's not my limits. I just do it in block form. So I'd build that, then I'd build another circuit, then I'd join this circuit to that one. And that's how I did all the electronics on this, because there's quite a lot of electronics systems on here for the whitewash system, for the cruise, for the stereo, for the MP3. And they were all done on a block system, then joined up with plugs. So it's not that bad. This is a tech video. If you want me to carry on, we're running into about an hour and a half now. If you want me to carry on, we're going to start building it. So that's the explanation of it, the best that I could do. And you build it on Vero board. This is like prototyping board. I'll snap this at a certain point where I think all the parts can fit. I'm not going to be using all that. But you solder this, so you put the parts in on this Vero strip. Let's get some parts. And here's our chips. Look, here's those chips I was telling you about, those timer chips. Look, there they are. Bought 5 of them. Only little, they're 8 pins, but you can put anything you want. So what I have to do is I have to look at the diagram, and I say, right, these numbers here, the legs of the pin. Now it always starts, they're always in the same order. It starts top left is 1, and then second down from the top left is 2, and you count down, then you go across and then back up. So I solder that chip into there, but I put it on a little socket actually, so you can pop it out. Here's the sockets. These are chip sockets there. So you put that in. You slot the chip in last so you don't damage it. So you put that into the board, then you turn it over, then you solder on here. Then some of them, legs and tracks, you don't want to be joined, and you use this little cutter and you can cut the tracks. Then you put little jumper links in, and what you do is you copy the whole way that's laid out with all the parts onto this board and solder them all in. So you make that circuit onto this prototype board, and you end up building a board with all little parts on it that all follow these links. You could, if you wanted to, you could just use wires and wire the whole. You don't necessarily need the board. You could bend all them pins out. I could solder loads of little wires on there, and these wires would be exactly this. In fact, I could actually physically lay the chip over here like that and put all my parts physically in the same positions like this, and actually make a physical copy of that, and it would work. Other than these pinouts will be in a different order, they might not go in, that's done schematically, so it's for ease of use. One might be up here and you'd have to cross the wire around. But the theory is you could lay that out. So my brain, all it has to do is convert that onto a layout here. And how you do it is you do a section at a time. You start with your main chips, put them in. You populate it with those chips. Then you say, right, I'm going to do some of the resistors. I'll do the resistors first. Then you just cross each one off as it goes. I just put a little cross through it to know I've put that part in the board, and you build that up. And then you test the board. Then we'll have a board, time switch board and everything. So what I'll do, I'll call it a day for this video. This is just really effectively me live chat. This is a live chat. It's not a fun-packed video. I could have done this on an audio only, I suppose. So I'm sorry that it isn't that, you know. That it's not high action, but as soon as them Cortinas start appearing, I'll be back out on the road. As soon as there's a rusty one in the shed that we don't have to furlough. Don't forget, it's locked down. I'm stuck. I've had 2 cars I could have looked at. There's a big 6. There's one in an old shed abandoned. I can't get there because the people don't want me around. They're all elderly people. I don't want to go there and upset them. I mean, I tried to say, look, just leave it open. I'll go down into the field and look at it. But it's not fair putting people through that. So we can't get the material at the moment. We're struggling for material. And I don't do road tests. I mean, someone said, well, you can go out and you're a really good car reviewer. I said, well, if I like the car, I am. But I'm not if I don't like the car. I'm rubbish if I don't like the car. You can tell that I don't really mean it. It's not sincere. So I can't really do that. I'll leave that to the people who do the car reviews. It's not me. Problem with my job is, the good thing about car reviews is it doesn't cost any money. People will give you the car and you can do it without big outlays. For stuff like this, you've got to go on eBay, you've got to go and pick the Cryptons up to try and get the material coming in. But that's just the way it is. I'd do it anyway. So, you know, I'd do it whether I was filming it on YouTube or not. I'd still be doing this. This is my hobby, which I enjoy. And I'm sorry that it is a bit complicated and you've not got that hardcore car Pete up to. And I'm going to lose people because a lot of people subscribe to see the car restoration work. And if you're not supplying that, they tend to unsubscribe. My subscriber level's not gone up. It's just stayed the same for the last year. So I've not gained anybody really. So, you know, it is tricky. It is tricky. And it is tricky with lockdown. We're on a lockdown. And everything that you do, you've got to think, do I really need to do it? And there's so many journeys I'd like to make that I don't. This, I class as essential because it is my living. I said it's my hobby, but it is also a revenue for me on YouTube. Well, Patreon it is for sure. YouTube, it trickles in. Patreon's really great. Without that, I'd be really screwed in terms of it just wouldn't be worth it. And if you're travelling out to get your parts, then it's for my work. And I've met nobody. You know, there's bulletproof bloody glass at CPC. I met nobody. I just fuel up once for the whole week in the car, so I have to make one trip to the petrol station. And I think that's just me being sensible. Someone said to me, oh, you shouldn't be out. I should be doing what I think I should be doing. I shouldn't be, not should, anywhere, if you know what I mean. There's no you shouldn't be out or you shouldn't be doing. It's about why, what am I doing? What's this car doing when it drives? What harm is this car doing? Oh, if it breaks down, then someone's going to have to come out and recover it. All that kind of crap. Garbage. Absolute garbage. You know, you've got to be sensible here. Absolute garbage. Yeah, if you're sticking your face in someone else's face, you don't want to give them coronavirus or a cold or whatever it is. You don't want to give that to someone. Whatever it is, it's pretty, you know, pretty nasty, fluish, coronavirus type bug. I don't want it, and I don't want to give it to anybody else, you know. And whether or not I believe in it is a separate debate, which you could talk about that. You could talk about astrophysics in the same breath, because you could just say, well, you know, I don't believe the Earth's round, and that's a totally different thing. I'm not interested in that. I'm just saying common sense is that I won't wear a mask in the car because there's nobody else in the car. I'll put it on when I'm near somebody so that I don't offend them, and I'm respecting people's views, and I'll wash my hands. And I believe in that side of it. I do believe in that good hygiene and respecting other people's wishes. I believe in it, and that's what I've done. But even when you're doing that, you're still restricted for what you can film on YouTube, because there's loads of things I could have gone out and done, and I've not done them. I could have done them, but I just don't want to rock the boat or take the Michael. You know, I'd do a lot more, and so would everybody else. So we're all got in it. There's not much I can do. We don't mention the C word. I'm going to go on that basis. Hope it wasn't too technical. It probably was, and you're going to kick me arse for it. This week's not has been as fun as we'd get, and we really are into the realms of tech talk with Pete C from Cortina City. Leaving you now, probably undernourished, but I will try and make up for all of this. The action could well get started again. We've got an auction coming up in April. How they're going to get around it, I don't know, but it's at Manor Park. We've got that. There's a few other little topics on the line. I can't get the car from South Africa because he can't get from Canada to Guyana to get it on the ship. So even that's buggered up. I'll talk more about that on next week's film, but you'll see that built. You'll see us build the circuit board next week. We'll populate all that, and I'll show you it power up, and we'll fit it to Ruby. That gets Ruby nicely fully automated on its lockup, just like Brambles is. And by the way, you saw that clip earlier on, cruising like a dream, as always. Pete C from Cortina, leaving you now with a long tech video. Take it easy, have another drink, and don't forget a pint of water before you go to bed. Vitamin B will help. If you can get yourself some vitamin B, it really helps with your alcohol, because alcohol stops your body from absorbing vitamins. So you need to top them vitamins up and get your water down you. See you soon, Pete C, signing out. straps, aren't they?
Maybe some new ones.
High-vis wheel straps.
Yeah.
We are loaded, so we'll catch you on the motorway. See you in a bit. Off we go. A lot of people interested in this car. Everywhere we go, people are stopping me. It's not for sale.
We had a crowd starting to form at the services, so we had to go.
Wow.
Otherwise, we'd have been there all day explaining it to everybody.
There's your sills.
Right.
There's your sills.
Oh, excellent. All right.
It's self-serve through the window. Look, I'll get inside. How many sills do you like,
So
sir?
screaming that.
Self-serve. Oh dear. It's good, isn't it? Like what we've done with the place.
Excellent.
Like what we've done with the place. Looks alright through here, but then when you look at it, it looks like a wrecker. Bit of photoshopping on that and we're good to go on eBay. So Jim, first impressions, what do you make of it?
I think it's great, Vic. I think it's great. I'm
All ready for the yacht?
being brave, mate. There may be a few.
So we've got the Newster on. Just check that engine bay out in a minute and you'll just see all those goodies. We've got little Newton, he's in there for the Sunday show. Someone said it's got the wrong foliage in it. That's done it. We're just having a pint here now inside the Maize machine. We've got Adrian joining us. I hope it is Adrian, else I've been calling him the wrong name for the rest of all of his life.
Transit car restoration show is now closed. Could all visitors please make their way to the nearest exit?
Spit and polished. Right. Oh my god, look at that queue.
How much do you use for that to get that finish?
Teacup 2000 special with a bramble finish.
I thought it was Teacup 83 you used on this one.
This doesn't look good, Dave.
No. Seem to have come up to
we have to get a charge on. Fuel level's not fantastic.
Ask him, see if we've got any. He's going to say go back through this queue in here. I can see it coming.
Oh mate, what's the trailer park that way, is it? Lorry park 9A.
All right. Cheers. We'll try this. This blocks his traffic. He might know.
God, we're not having fuel for this kind of thing. Holy shit! Where's the truck? Where the fuck is the truck?
I don't know. Oh, that's out of the yeah.
Right, get it through.
Go back in.
Front. We're doing for 28 mile an hour. Kick down! Kick down! Did you hear that kick down?
Yeah.
The thing kicked down!
Just gotta keep going. We've got to keep going. Go forward. That's the bloody. We've got to go back into there.
Yeah. We're back in there, mate. Sorry.
Got to go back.
I'm not even. Yeah, I've got to be back in there.
We're on public road up there. We're not allowed on public road.
Right. Thanks. Jesus. Rambo.
Don't go so fast if cars coming this way.
Keep your eye on the screen. Why couldn't we just wait in the hall until everybody had gone, Dave? Now they're off road, so we're okay. We're moving here actually. Now, can you see it? Can you recognise anything, Dave? 4, does that mean anything?
No, don't look at them buildings. It needs to be to the other side of these buildings.
Right, there's an official vehicle on your left. I don't know what it is. 4.
To the left-hand side, if you can. Oh, look! This is where we should have come out.
Trailer park.
Cheers. Thank you. This is the way. We can't have got to public road.
This is public road beyond these barriers, I'm sure of it, Dave. North 12.
What the fuck?
Exit Litchfield. That's the I cannot do it, Dave.
Right, we'll park up. I'm gonna.
So we're going to say I've totally fucked up by bringing Sunday's tickets instead of Saturday tickets, so there's a gang of people outside who can't get in. And what I have got is a pair of swimming trunks. Absolutely no idea why. Well, swimming trunks and no tickets. There you go, there's the evidence. Sunday's tickets. Saturday, people outside waiting to get in. Shit!